What did we learn last week? Okay, what's the purpose of FEA? Why did we learn that, right? Because it reduces a lot of testing, so we can simulate everything into computer numerically, so which save money, time, and also it save a lot of lives, okay, enhance safety. So we gone through the notes on how to develop the rod elements. What is the stiffness matrix? What is the stiffness matrix for the rod element? It looks like this. That's the stiffness matrix for the rod elements, okay? And then on this, we went through some examples. Then we learn a new element, which is the rod element at an angle. And right here, we developed how we come up with the truss element matrix, because we use the trigonometry matrix, the transformation matrix, to tilt the whole truss at one angle and an angle. And then with some matrix manipulations, we developed the stiffness matrix for the truss elements. Okay, to me, the best way to learn something is do more examples. Would you like to have some more examples? Okay, as I promised, I'm gonna have a few more examples on rod and truss elements. Okay, let's go through some of the examples in the textbook. Okay. One of the questions in chapter 1, question number 4, one of the questions looks like this. Okay, this reference. Okay, there is a spring elements family, okay, with in total 6 elements. With 6 different K. Okay. At the end, it's fixed to the ceiling. And then at the bottom, it's being pulled by 500 pounds of force. So what is the first step when you approach a rod elements problem? Name the elements. We have named the elements already. K1, 2, 3, 4, 5, 6. And then we name the note, which is very important. Note 1. Okay, how many notes do we have here?
4.
Okay, technically there are 4 notes. Well, technically there are 5 notes. Okay, however, they're tied together, right? This note is tied, the whole mass right here is tied together. So we only call them one note, note 2. Same here, right here, technically there are 5 points, but 1, 2, 3, 4, 5 points, but they're tied together. So we call them note 3 only. And then finally, at the end, clearly it's only one note, so it's note 4. Okay, the next step, we write down what is the stiffest matrix for each mess up, for each mess. For
Chris,
yes, what's up?
if I'm assuming if like K1 or K6 wasn't symmetrical in the middle of all the Ks, then you'd have to interpret it as multiple points. Would that be true?
If they don't tie together, yes, there are multiple points. But right here, okay, if this note attached to K1 is moving, what about the others? They move along, right?
Yeah. Well, no, but I'm saying like if K6, the loaded element, was aligned with K2 on the far side, but the rest of them were tied together, would you interpret them all as one piece still, or doesn't matter?
Yes, there is one piece. Yes, there's
Okay.
2 elements, but one piece. 2 elements, but one note tied together. Okay. Okay, now let's define the local matrix. The local matrix right here, local. For the first element will be K1, K1. Okay. Do not develop it for me, okay? Because we already developed this matrix from the note in week 1. Okay, you don't have to develop it one more time. Okay, right here, K2, 3, 4, 5, they're joined together. Okay, so instead of a K1 is only one element, right? But K2, 3, 4, 5, they are one element, 4 elements moving together, which is working as a thick spring. But what is the stiffness for this? So let's assume that it's called K big. So you can join them together as a stronger spring. So the local matrix for this mass will be K big. Okay, finally, the bottom one. Very easy. 6, K, 6. Okay, now it's very important here. Now we have 3 local matrices, but what notes do they look after? For the first matrix, the notes they look after is the note 1 and 2. Note 1 and note 2. The second matrix, the thick, big matrix, looks after nodes 2 and 3, nodes 2 and 3. The bottom one, it looks after nodes 3 and nodes 4. So instead of a 6 element, I have turned it into 3 individual pieces. Okay, and each piece looks after 2 nodes. The first matrix looks after nodes 1 and 2. The second matrix look after nodes 2 and 3. And finally, the bottom one looks after nodes 3 and 4. Now we have all the elements. Let's put them together. Okay, guys, tell me, what is the size of the global matrix in this case?
4 by 4.
Correct, it would be 4 by 4. Okay, for the global matrix will be nodes 1, 2, 3, 4. And 1, 2, 3, 4. Okay, let's put in the first one. It will be K1, K1. Okay, please note. Okay, there's 2 elements, but they share the same node. So right here, K6. Oh, I'm sorry. Okay, tell me, do you have any questions so far? I have 3 individual local matrices, and I join them together. Okay, we write in the force vector, the displacement vector, U1, U2, U3, and U4. On the left side, we have force 1, force 2, force 3, and force 4. And then let's apply the boundary conditions. U1, sorry guys, KB and K big, same thing. You know, I just too lazy to write down IG. Yeah. And now let's apply the boundary conditions. Let's always do the displacement first. Okay. Say it again. How did you get here? The combine 1, 2, 3, 4. Well, we have 6 elements, right? But they join the same nodes. So I join them together.
But sir, why wouldn't you add the K1 to the KB?
Why would I? Say again?
Why wouldn't you? Why wouldn't you add the K1 on the first column to the K big? Or are you just adding 3 elements? Is that why?
Because KB is not involving node 1. KB only looks after nodes 2
that
and 3.
sense. That makes sense. Yeah.
Right? And same here, K6, it doesn't go to node 1, 2. So it only goes to K3, node 3. Now let's apply the boundary condition. U1, 2, 3, 4. U1 is not moving at all. 0. Okay. And U2, 3, 4 is moving. And then on the left side, we know on the left side, we know F4 is negative 500 pounds. Okay. What about F2 and F3? There isn't any force applied to it. Okay. There might be some internal force struggling between K1 and KB and K2, KB and K6, but there's no applied force on it. So it's 0. And finally, F1 is a reaction force attached to the wall or to the ceiling. So now we have four
Can you say
equations.
that forces 2 and 3 are 0 though? Like there's still force going through nodes 2 and 3.
Yes, correct. There is some internal struggle between between K1 and K big. There's some internal struggle between them, but do you see any additional externally applied force on it? In a global point of view, there's no applied force on nodes 2 and 3, right? So I cross them away. So now we have 4 equations and 4 unknown. And you can solve them and look for U2, U3, U4. Do you have any questions here? Can I move on?
Chris, I was thinking we would find the F2 and F3 too, because in a way F1 is also more of like an internal reaction force, right?
Globally, there's no applied force on nodes 2 and 3. But when you write the free body diagram, K1, K big, K6. When you draw the free body diagrams, there is some force on it, okay? But they cancel each other globally.
Okay.
Same as the other side. You know what? Right here is 500 pounds, right? I guarantee you right here will be 500 pounds as well. Because why? The whole assembly is not moving. If the force is not balanced, the whole thing is going to fly away. Any questions? I want to show you one more example.
Is it really wrong in that case to assume that you know F1 then? Or your reaction force?
It is very wrong to assume it so early, because this is a problem which is very obvious, right? Which is so obvious. It's only one one is one vertical assembly, okay, and the reaction force is so clear. It's 500 pounds, 500 pounds to the bottom, and it's so wrong to assume it's so early. You should go through the matrix, solve the equation, and solve for R. Good one, good questions. I'll show you one more example. You know that's gonna tell you, just never assume too early. Okay, this is gonna be a reference homework 1.6. Okay, can I move on? Because if you have problem with this one, you will not understand this one though. This coming up. Okay, ready? Let's go. Wow, what a mess. Okay, does it confuse you? Okay. Okay, guys, tell me, how many elements are there?
6,
6. What about note?
5,
4, 5. 5 note. Okay. Any questions so far? Okay, let's move on.
Somehow make it 4 nodes,
Why is that?
Yeah.
because K4 spans all of K2, K3, and K5. Is there some way that we could combine all that?
Let's write it out. When this argument, the best thing to do is write it out. Note 1, note 2, note 3, note 4, note 5.
Okay, thank you.
Okay. Okay, the local matrix for note. Okay, the local matrix that looks after note 1 and 2. Let's see, right here. K1, K1, negative K1, and negative K1. Then I have a matrix that looks after nodes 2 and 3. Aha, right here, it becomes a big matrix. 2 plus K3 minus you know what? Let's call it K2 plus 3 minus K2 plus 3. And then I have a matrix that looks after nodes. Oh, you know what? Right here. 2 and 3. And then I have another matrix that looks after K4. Nodes 2 and 4. And I have 2, 5. That is node 3 and node 4. And finally K6. That will be node 4 and 5. Guys, do you have any questions so far? I have simplified the whole mess into 5 elements, and it looks after 5 nodes.
Chris, can't we make that centerpiece into like a one giant matrix? K2, K3, K4, and K5. K2 and K3 in parallel, and that big in with K5 in series, and then with K4 in parallel.
You only join them when they are in parallel.
Okay.
Because right here is too much work. I see what you mean. Right here is too much work to join them together. We'll join them now. Okay. I'll show you. We'll join them globally. Okay, I'm gonna move the chat box to a side. You have any questions? Speak up. No. Did I miss any questions? You know what? Just if I'm not gonna read it for now. You know, if you have questions, let me know right away. Okay, I have a big global matrix. Let's fill in the blank. K1. Okay, node 2 is K2 plus 3 minus K2 plus 3. Okay, that's done. That's done. What about K4? K4 looks after nodes 2 and 4. Okay, so will be plus K4 minus K4 minus K4. But right here is K4 positive. And K5 looks after nodes 3 and 4. Will be K3 will K5 negative K5 K5 plus K5. And finally, K6, it goes right here. K6, negative K6, negative K6, and K6. Guys, seriously, for any FEA problem, it takes a lot of patience. You know, just be careful and enter each one correctly. Okay. So, do you have any questions so far?
Professor, I find it easy to develop global matrix like we did last time with the force is equal to K1 multiplied by U1 minus U2.
We're doing that right now. We're doing that right now. No, the left column is a force matrix.
No, but we skipping that equation part, right? So.
Oh, like U1 minus U2, and then
Yeah.
you don't have to develop it for me. Okay. The first lecture I showed you how I get there. What did I do to get K1, and negative K1? I have developed that already. Now it's time to use them and how to join them together.
Okay.
Okay. So
Uh,
any
sir,
questions?
could you
Any-
explain how do you join the K4 again?
How do I do the K4?
You join the K4 part?
Okay. This column looks after column 2. Each column looks after one node. Okay, and K4 looks after what? Node 2 and node 4. Correct? So I put the entry K4 here. 4. Is that good?
Yeah, thank you.
Okay.
So in this
Appreciate
case, when you have the 10 libs of the 10 pounds applied, is that global then, or those aren't internal stresses at this point, right? Because they're stated. So we can't say there's 0 at notes 2 and 4.
Okay, here's a hint. You know, all the global force is very visible. All the internal force struggle within the system, you cannot see that. You have to solve it out. Let's say you're standing, you're working, you're writing. The total force that exerts from the muscle to your pen to your shoes is very obvious. You can measure that. But the reaction force, the internal force between your bones, every little joint within your bones, you cannot see that. You have to solve it. Okay, let's apply the boundary conditions.
Chris, in column 2 and row 2, is that K1 plus K2 plus 3 or minus K2 plus 3?
I'm lost.
In column 2, row 2,
column 2, row 2 is K1 plus K2, 3 plus K4.
Okay, because in the matrix above, it's minus K2 plus 3, right?
Matrix.
So for the second matrix and the 5 matrices you drawn
Okay,
above.
for the second matrix, I have K2, 3. I put it right here.
Oh, it's that one. Okay.
Yeah,
Right.
right here. And the diagonal term K2, 3, I locate it right here.
Okay.
It's good?
Yep.
Yep. Okay, now it's time to apply the boundary conditions. Let's do the displacement first. Okay, we know nodes 2, 3, 4 is free to move, but U1 and U5 is 0. Okay, what about force? Force 1 is attached to the wall. There's something that attached to it. I don't know what is it, but nodes 2 I know is 10 pounds. Nodes 3, there's no force attached to it. Globally, I don't see any force. Okay, internal force, I don't care. We can solve for it. Nodes 4, we have 10 pounds. F1 and F5, I cannot say that they're 0 because they're attached to the wall. There's some force attached to it. And now we have 5 equations and 5 unknown. And we solve for it. Solve for U2, U3, U4. Any questions before we move on?
So how do we know that the 3 is 0 again? The force?
I don't see any applied force on node 3.
Okay.
So globally, the applied force is 0.
Yeah.
But it's different from node 1 and 5. 1 and 5, there's no force on it, right? But they're attached to the wall. I know there's something going on. Okay. Another hint is usually
That's 1 and 6, no? Node 1 and 6 are attached to the wall.
1 and 5. I don't have node 6.
What is that K6 again? Oh, yeah, sorry.
K6 is the element.
Yeah.
K6 is the element, looks after nodes 4 and 5. Very cool.
Yeah. Okay, thank you.
Okay, so we just gone through 2 examples on rod elements. I think that's enough. Yeah. Let's do some work on a spring element. Oh, sorry, truss element. Okay, I want to know, do you have any questions on how you develop this truss element? Yeah, if you don't understand it totally, it's okay. Okay. But you must know how to use it. Okay. Again, now is a reference homework from our textbook. Okay, I have 2 elements and an angle. The pounds. Okay. The total length of it is 10 inch. 10 inch. Let's name them. Okay, I have 2 spring elements attached together at an angle of 60 degrees. Okay, and the force is applied on the end of it. 200 pounds applied to the end of it. And we need to define and calculate how much it deflects. Yeah, I will upload it. I'll upload that lecture. Well, it's not the best format, but I'll upload it. Or maybe I'll email it to you guys. Okay. Okay, so we are exerting a force on node 2, and we want to calculate the deflection in node 2. So what is the first step? We name the element system. This side is the elements number 1. This is elements number 2, and I have node 1, 2, and 3. Then we will EA.
Professor,
So what is K? Yes, what's up?
In the question, I haven't looked at the question yet, but are we going to be given this figure, or do we have to create it from the instructions in the question?
The figure will be provided, but not necessarily the elements and the node number.
Yeah, that we have to do it. But yeah, because the base figure will be provided, right?
Oh yeah, I'll give you figures, you know.
Thank you.
Now, for any truss elements matrix or truss elements problem, I prefer to see an information table. Trust me, it is good for you, good for me, you know. So I want to see how you think. And I can mark you accordingly, okay? For the information table, what does it include? Nodes number, as a theta. What is C? C stands for cosine. S. Once you have C, once you have S, you calculate the C squared, CS, and S squared. Let's look after the first one first. You know, elements number 1, it goes from node 1 to 2. Node 1 to 2. Okay. And the theta from node 1 to 2 is 60 degrees Celsius, 60 degrees. The cosine of 60 degrees is a half. Sine of the 60 degrees is √3 over 2. So therefore, C squared is 1 over 4. CS is 2. And S squared is 3 over 4. Do you have any questions so far? It's very important.
Wouldn't CS be √3 over 4? That's a cosine times sine, right?
My fault. I'm sorry.
No, that's fine. Thank you.
Good catch. Okay, let's move on. Let's look at the elements number 2. Okay, elements number 2 is from 2 to 3. Two to 3. From node 2 to 3 is negative 60 degrees. The cosine of it will be hold on. Cosine of it will be 1 over 2.
Professor.
Yes, sir.
So if you do from 2 to 3, wouldn't the angle be positive then?
Well, if I go from 2 to 3, this is 0. Okay. This is 90.
Oh, okay, never mind. Okay.
Right. But I think I made a mistake in my note. You know, instead of a 2 to 3, it should be 3 2, 2. So it is 120 degrees. Yeah, correct. From 3 to 2. So you go past 90 degrees. Okay. And from 3 to 2 is 100. -1/2. The sine will be √3/2. √3/2, and then c squared will be 1/4, and cs will be -4. And this side will be 3/4. Okay, K1 will be 1 times 10 to the 6. The first term will be c squared, 1/4. Second term right here diagonally will be s squared, which is 3/4, 1/4, and 3/4. And then this term will be cs. And right here will be cs as well. That term will be cs. And this term will be -cs. I'm just using the formula provided in the note, plugged in all the variables. What did I miss? Oh, right here. So that one, that term's -c squared. Right here is -c squared. C squared. Finally, this is -sc. And this term will be -s squared.
Sir, I'm worried about the way you change the nodes. If you're doing 1 to 2 and 3 to 2 instead, will that just like change their position in the matrices? Like once you combine like the
When you
two
combine
different
them.
matrices?
Oh yeah, you can do that. Yeah.
So it doesn't matter.
I'll show you later. No worries at all. Okay. That one looks at the note 1 and 2. Note 1 and 2. Okay. Number 2. 1 times 10 to the 6. If you feel more comfortable with doing notes 2 to 3, it's okay. Go for it. You know, I made a mistake in my note. I'm going to correct that and upload it later. Okay. Right here, you know, with the matrix will be. I always do the diagonal first, right? So 1/4, 3/4, 1/4, 3/4. then the next step will be SC. This row is all SC. Okay, SC positive. SC negative, and then SC positive. Okay, they are always diagonal symmetry. So whatever you write here, you write the same thing along the symmetrical line. And then 3/4, and then root 3/4, and you write the same thing. Okay, let's do a check. Make sure they are symmetrical. Yes, they are. Okay, and here's very important here. It's note 3 and note 2, and note 3 and note 2. Okay, this is how I do it for 120 degrees. But if you feel more comfortable with notes 2 to 3, it's fine. Go for it. But I'll show you how I put it together. So I'm gonna make a big matrix and name them 1, 2, and 3. 1, 2, and 3. And then you just write the whole terms, same thing there. Basically, this box, I just copy the whole thing to here. I need a longer box, so yes. Okay. So note 2 and 3, we will inverse that. So this box comes to right here. 1/4. Okay, and then this box, look after 2, 3. It goes to right here. This box okay, here's the tricky part. Okay, this notebook looks after notes 2 and 2, so it goes to plus 1/4 minus 3/4 and minus 3 over 4 and plus 3 over 4. So guys, how you doing so far? Did I confuse everyone?
Just on the second part of it, where you did the K2.
Yeah.
You know how you have on the K2 on the top, the first matrix, it takes care of 3. So column says 3, and then on the row it says 2, right? It should have been on the box below. It should have been on the right hand side middle, right? Because it says 3 on the top and then 2 on the side. Shouldn't that go in there instead of like at the very bottom, the arrow you're pointing at? Shouldn't it go just one slot up because it's 3 and 2? The way you
3
named it.
and 2. Okay. This box come from there. And
Shouldn't
this
it come from like the left hand one?
right here?
Where? Okay.
But guess what? They are symmetric, you know. This term and this term, they're same thing.
Oh, I see. So if you drew like a 2-3 matrix instead of a 3-2 matrix, it would look identical.
Yeah. That's right.
That's the case. Okay.
Yeah. But the key things, right? The key to success is right here. Make sure you add the matrix together and make sure this entry point is the sum total of nodes 2. All right. Do you mind if I erase the line? Because I want to draw the vector force. Sorry, the displacement vector. What is the displacement vector for the truss matrix? Because each one has the nodes, right? And each node move in the x direction or the y direction. 2, v, 2. Usually I name u as any horizontal movement and v as any vertical movement. Same here, we have F1x, F1y, force acting on a node in the x and y directions. Cool. Okay, and then U1, I know it's not moving anywhere. And V1 as well, because the node 1 is totally tied together. Node 3 as well is 0. It's just tied together. Okay. And I know V1, force 1 and force 1 in the x and y direction, there will be something. This is attached to the it's attached to the ground, right? So I cannot set anything F1 and F3 into 0. However, I know F2y is negative 200 pounds. What about F2x? I don't see any force applied to F2, applied to nodes 2 in a horizontally. Well, this is 0. And then we have 2 equations and 2 unknown, and we can solve for U2 and V2.
What about f1x and f1y and
It's
same
a-
thing?
It's a reaction force.
So we don't have any applied force, right? So
We don't have any applied force, but we know we cannot set it to 0 because it's supported by the floor, by the ground.
so we don't consider this as 0, right?
No, you cannot. You cannot.
Can we not assume that the displacement in x is 0 for point 2 because it's symmetrical?
You're jumping ahead. I do want to show you one more example. Same problem, but now I'm not gonna write two local matrix. I'm gonna just work on one, because you're right. When I look at the problem, the whole thing is symmetry, right? Okay, I call it note 1 and note 3. Okay, what is the applied force? Up there, we have 200 pounds, right? So now it's only one side. So it's only 100 pounds.
This only works if your stiffnesses are the same, right?
Correct.
And just
Very
another
good.
thing that's important too is if your K1 and K2 weren't equal, you'd have to equate them before you put them in the total matrix, right?
You must ensure this is symmetric. Okay, if one truss is thicker than the other one side is fat, the other side is thin, you cannot do that. You have to make sure they're identical matrix. Identical truss member. Then you can apply the symmetry. Okay, right here, I just write down the same matrix again. I don't have to add any matrix now. I just use the same one up there, okay? Okay, I'm not gonna write the whole thing, but I want to show you how I apply the boundary conditions. Okay, I have U1, V1, and U3, V3. F1x, F1y, and F3x, and F3y. Okay, U1 and V1 is 0 because it's mounting on the floor, nothing, right? U3 is 0 as well because it's symmetric, okay? So U3 is not moving to the side. It's not going anywhere on the side, but it's allowed to move vertically, okay? V1x and V1y, I know it's being supported by the floor. I cannot set anything to it. Now,
So for the previous example, can you not say that the horizontal movement at note 2 is also 0? We didn't state that in the last one, but you could probably do that as well for U2. Yeah, this question right here, you stated your boundary. There's no movement at U1 or V1 or U3 or V3, but then if you're going to say that there's no movement at the horizontal movement for the node 2, then you can say it there as well, right?
well, okay, technically you're right, but up there, okay, I assume they're not symmetric, right? I do not know. I let my formula tell me there's no movement on node 2 on a x direction, okay? But right here, I chop it in half, and I must know, I must set up the boundary conditions and saying that U3 is 0. Right, basically up there, I do not set up the boundary. Do not set up the boundary conditions on a symmetric boundary condition yet. But at the bottom, I assume they are. Okay, so that's why I said U3 is 0. Okay, because I said U3, oh, good call. You're right.
Yeah, that should be 2, right?
2, that's right. Okay, happy? Now, U2, because this is a boundary symmetric BC, okay? And because this is 0, I cannot set this to 0 now, okay? There's some force pushing it to the left to make it 0. And finally, right here is a negative 100 pound. And then you solve for V2. Any questions?
So can you equate F2x to F1x then? You can say that the x component at node 1 is equal to the x component at node 2. Because we know that that's not 0 then.
F1x and F1y is
To
not
move-
0. Not 0.
Okay.
Okay, we just did 3 examples on rod and truss elements. Let's take a short break. Okay. And let's come back to class at the 10:30. Is that good? 10:30, and I'll show you something new. Is that good? All right, guys, I'll see you soon.